Hi, Chinthaka.
Hello, Boby.
So last class you were mentioning about this capacitive sensors.
Yes.
In fact, what you said is if you have just two conductive plates separated by some insulator, that's all it is needed. For a capacitance to form.
Pretty much, right? Yeah.
And then it is up to you to make use of it.
It's true.
Sign sensor and so on.
Yeah.
But one thing you said, if you have a parallel plate capacitor, let's say like this. Let's just go like this. You have two terminals coming out.
Yes.
And then you said if the area of this is A, and then the distance between this, if it's D, I think you gave some expression for capacitance.
Yes.
Is equal to
Epsilon 0, epsilon R.
A by D.
Yes.
Yeah. In my drawing, both areas look different, but it should be the same. Now, actually, I tried to, I took two electrodes like this, and then I connected it to LCR meter.
Okay.
So it had two terminals connected like this.
Okay.
And then I selected to measure
Capacitance.
So I know the area of D, etc. I didn't introduce any specific insulator. There is just air.
Yeah. Okay.
So epsilon R is 1. As per calculation, I was getting about, let's say, 10 picofarad. But this reading was showing slightly more.
So LCR reading was
The LCR meter
slightly higher than what you measured.
It was showing. I cross-checked my calculations correct today.
Yeah.
So I thought of asking you what is wrong.
So there's somehow some extra capacitance that's added when you're measuring with the LCR meter.
So is it something, is this equation correct?
That's a standard equation.
Yeah.
So technically,
maybe it is derived under some approximation.
Maybe some ideal conditions, maybe.
Correct.
So when you connect this to the LCR meter, you have some cables, no?
I have some cables.
Yeah. But they're not very long. Standard cables, right? Handheld LCR meter.
But I think it was some about maybe few centimeter, maybe 20 centimeter, 20, 30 centimeter.
Okay, so not that long. But could that add some capacitance? Why? Cables. So
cable, but this electrode is, equation says about this over here.
The equation doesn't say you get it if you use a LCR meter.
Okay. So what you're saying is this cable is also two conductors and this also separated by some distance.
I guess so.
So there will be some capacitance here also.
That's what I'm thinking.
Yeah. Cable capacitance.
Yeah.
Let's say I corrected for that somewhere. Still it was not much. See, I first measured the cable capacitance. I got some value. I subtracted that from whatever I measured. Right. So then it should match.
But it still didn't match.
No. So definitely cable capacitance is an issue.
But it did not make a significant difference to
There was some value.
Some value. Yeah.
But, I noted it and subtracted it from subsequent.
But you still did not get 10
I didn't get 10%. It was slightly more. I remember you showing some figure. Some electrode like this, and then you're drawn something like this.
Electric field.
Electric field. Okay.
Yes.
So, how the electric field of this will look like? I mean, if it's just two parallel plates. Now onwards, I'll not try this 3D. Let's say these are these two electrodes. So will this field be just like this? I remember from your Hall effect.
Yeah, the field will be like that, but also at the edges, there'll be
also this is around between those two electrodes.
Yeah, so I mean directly between the electrodes, yes, there will be an electric field, obviously.
Then what you're saying is there may be some here.
Some, yes,
like this.
some fields at the edge.
Like this.
I think we showed that as well in the...
this meter doesn't know about it.
The meter doesn't. I would have thought the meter would have compensated for them.
But
no.
How will the meter know? There is some design, I may keep these electrodes closer, some may be away.
That's true. So it would change according to that.
What is it field called?
I believe this is called fringing.
Okay.
Electric field. You can also have fringing magnetic fields, I think. But in this case, it will be a fringing electric field.
Okay. So this will also result in some capacitance?
I believe so. It does. The electric field, right?
So then this must be the reason.
That could be.
Because your calculation takes care of epsilon or A by T.
True.
I can see the field going beyond that.
That's true. And you're getting some output that reflects that.
Yeah. And this one, this is 2D. I mean, in the 3D diagram, it is there.
Yeah, on all sides, all four sides. Yeah, that's true. So it's a significant addition, I think.
And if the size of the electrode is more, this fringing may become
even larger than the field between. Yeah.
Relatively larger compared to.
That's true. That's true.
Possible.
That's true. And normally we keep the distance very small anyway.
Yeah.
Right?
Yeah.
So, so I think you're getting at something. That could be the reason. But how do you measure that?
Maybe difficult. Because it comes along with, it's not separate.
But then how do you compensate for this?
I don't know whether it's possible to compensate itself. But maybe there is a way to calculate or measure or make some changes so that if at all you want to remove the effect of it, there may be some way.
So you're saying this kind of thing happens if you have just two electrodes like that?
Yeah.
What if you just take a capacitor? That will not happen.
That will also have
some fringing field.
Yes.
So if the capacitor, for example, says 10 picofarads, you measure, you might get something slightly higher.
No.
No.
So that when a capacitor says 10 picofarad, for example, it must be already measured and then.
Okay. So that's what you not using the equation.
I have cut the electrodes, etc.
And then
set it everything.
Right.
Calculated this. And then see, it could be there could be various reasons. One, you said, okay, the cable capacitance CC. The other one, the meter itself can have some error.
Some error.
But then we found there could be this fringing field also.
Correct.
So it may be that I can make use of this fringing field for some sensing application. Why not?
That's true.
Yeah. But since you said, can I have a design where this fringing field doesn't contribute to the capacitance that I am interested in?
Right.
Is that possible? Let's see.
So
I've seen some design. I will try to draw that. let's say this electrode is there, the top electrode.
Okay.
Then they have introduced something surrounding it. Another plate surrounding it.
So when you say another place surrounding it,
On the same plane.
on the same plane, that means the middle is empty.
No.
Then
I'll try to draw. Let's say something like this.
okay.
Or the top, suppose if I draw a line here and then draw it.
Okay.
I have something at the center.
Yeah.
And then I will have two pieces here.
Okay.
They are not touching. There is a small gap. So, maybe to make it clear, I have one electrode here, which was the one originally present.
Yes.
Then another conductive surface is introduced. So
it's not on top of each other.
no, it's on the same plane, right? Then, of course, there is the bottom electrode. Maybe I use the same color. With the required distance d, etc.
So the second electrode that you add, right? And where the first electrode is, right?
So I have one connection from the center electrode. Then I have one connection from the outer electrode.
But the outer electrode is not a full electrode in the sense that there is some space for the other one to fit in between.
Yeah,
right?
So that's what this figure, you see some small gap.
Yes. Yeah, that's what I meant. So there's some space in between the outer electrodes so the other one can, but they're not touching each other.
Not electrically
Touching each other, yes. Okay.
So we can assume there was a sheet there. I've taken, let's say I've drawn a square shape and removed that.
Yes.
Okay. Something like that.
Clear.
So I have like this.
Okay.
And I don't know how is it solving the problem. Maybe I can try to draw the bottom here also.
But this way you can measure some field between the two top electrodes.
Of course, I have the terminals available. That's true. Let's say this is A, B. A is here. B is here. And let's say this is C.
Yes.
You tell me what to do with this terminals. I go on. So like if you try to measure like this, right? That means let's say this is connected to some voltage. Let's say this is connected to ground. I need to connect the speakers.
Yes. You can connect to ground.
Yeah, if I connect to ground, actually there will be field lines like this.
Yes. Exactly.
Here shall I connect? Leave it like this, or
what if you leave it like this?
Then we don't know what voltage we have.
That's true. It's a floating voltage.
Correct. What if we connect to same BS?
Yeah, you can do that.
You can try that.
Yeah.
So suppose let's say this is also at BS.
Okay.
Then how will the field line look like? This region, I have no doubt.
Yes.
It will continue like this.
Yes.
Here onwards, I have small confusion because there is a small gap there. We can assume that gap is very small.
So between A and C, there will be some field, I think.
Yeah. So, I mean, let's say this gap between A and C is negligible.
Okay.
And they are in the same potential.
Yes.
That means it will continue to have this
Correct.
same.
Yes.
Correct?
Yes.
This side also.
Yes.
But then, of course, fringing will be there here.
Yes.
So that way, it is still there.
You pushed it
For
further.
the outer electrode. Right?
Yes.
I mean, it's kind of a ring.
Yes.
Somehow it is guarding the inner electrode.
Yes. But then your area of the plates, in this case, you have two areas there.
Yeah.
If you take
Let's say the area A, I have not changed for the inner electrode. Let's say this is still A.
Okay.
Bottom I have enlarged
Mhm.
to cover the whole thing.
Mhm.
Now, suppose if I measure this current, I will have, and let's say there is a current here, maybe Ix. Will Ix and I be same? Now, there is some current through the central electrode.
Yes.
There is also current coming from the outer ring. Both will go to terminal P.
Right.
So, I will be more than Ix.
I will be more than Is. Yes.
Yes, correct. So, that means there is some current through this. Maybe let's call it as IF. So, I will be Ix plus IF.
Yes. And that IF is due to that fringing.
It
Or the guard electrode.
It is for the guard ring, which also includes the displacement current flowing through the fringing field.
Right.
So, if I measure I, it's of no use. Correct? Because it has this fringing information again.
Yes.
But if I'm measuring Ix, that will just have the field present in this region alone.
Correct. Yes. Yes.
Because that Ix is the displacement current
For that area.
from the central electrode to the bottom electrode.
Yes.
There, if I do the calculation, it should match. Because the fringing field is not coming.
So you're taking out the fringing.
Yeah, so let's say that capacitance is Cx. Let's say Vs is at some omega. So Vs omega Cx will be Ix.
Yes.
Vs I know, omega I know. From the Ix I can calculate or estimates, measure Cx, which will match with our calculation.
So basically, this is this, what you have? Ps something, omega. No?
Yeah, Vs omega Cx.
Yes. So how much that changes, it's the ratio between Is and I. How much, see, you measured before, right?
Yeah.
And you did not get something, or you get something higher.
Correct.
So that increase in factor, is that related to that now?
So, no. What I'm trying to say is, if Cx is the quantity that I calculated using epsilon 0, epsilon Ra by d, and now I measure by measuring this Ix,
yes,
Vs and omega I know. So I calculate Cx.
And that should match that.
It will match with this.
Right. Okay. Yes.
Now, this C is also I'm indicating Vs. See, it may not be in a practical situation. It may not be Vs. Or now we have a source which is connected to this terminal, but it may be part of another circuit, correct? I mean, we don't know. This is coming from somewhere, right? So I may want to give this voltage to this. I mean, the sense like this.
The same voltage.
Yeah. Or what I'm trying to say is, when this current is coming from a source, that source may have some output impedance.
Okay.
The voltage Vs now may change if due to this IF, etc.
Okay.
I would like to, have no effect, I mean, due to this current. In the sense, I prefer not to draw this current from this Vs.
Right.
Is there a way to do this?
But you still want it equal to VA.
I want still this to be equal to VA.
Well, I is part of Vs, no?
Yeah. I mean, at the moment it's like that.
Yes.
But it could be supplied by something else.
Okay.
No, we wanted to keep these two at same voltage. So we could maybe use one voltage follower.
Okay. Within the circuit.
Yes. Yeah. We can just use voltage follower. So this voltage will also be Vx. Sorry. Yes. This can be connected to this.
So it will not
drop
from
the source. Right.
Okay. Yeah.
So basically we are driving, I mean, you could drive in different ways. One of the ways which is commonly used is this. You introduce a voltage follower. So that maintains the ring that you have introduced.
Yes.
At the same potential as that of the electrode.
Yes.
And then get rid of this issue related to fringing field. If it is required.
Right.
As we mentioned, in some cases, the fringing field may be the one that you are using to rising application. Right. But for example, in this case, suppose I am, let's say, changing the distance between this for sensing. Because as per the equation, I can maybe change A, change D, or change epsilon R. Correct. To use it as a sensor. So suppose I am changing D. When I change D, the fringing field will also be changed.
Yes.
So the capacitance that I measure is not just due to change in D. It will also be due to the modification that is happening to fringing field. And you don't want.
Yeah, and that might not be linear.
Correct. So that will not be. Yes. The D effect, D by itself is not linear. Because D is in the denominator.
Yes.
But this will introduce an additional unwanted effects.
Right.
So when I introduce a ring like this and maintain at same voltage, then this is
decrease of the
ring. So usually this ring is called as guard ring.
So, we talked about the coplanar electrodes.
Yeah.
Right?
Yeah.
And that pattern was repeated.
Yeah.
So if you have a sensor like that, would you have a guard electrode there as well? Because there will be some fringing field there too, right? At the edges.
Yeah. I think that design is a bit different because that's a planar design.
But there still be fringing.
Yeah. Because there you are what you're
you are using it for
right. Because you have cross section area, one electrode here, other electrode here, etc. And then you have this.
Correct.
Is here. Yes. Let's say this is at plus or Vs and this is at ground. Then it will be in this fashion. Yes. Also from here. So it is a fringing field that, and in fact you are saying to test permittivity of some material or a sheet or something you introduce like this. Yes. It will make a change in capacitance. But it is anywhere it is non-linear only.
Right.
and fringing field is the field that
So for that, we actually use the fringing field for sensing.
we make use of the fringing field or sensing.
Right. But here we want to get rid of it.
Yes.
Not get rid of, but compensate for it
Yeah,
rather.
yeah. It is still there, but your measurement of Ix is not affected due to the fringing field.
Correct.